Hello, and welcome to our 2:30 press conference, Alaska's Thawing Permafrost, Latest Results and Future Projections. Our speakers today are Vladimir Romanovsky, Professor of Geophysics at the Geophysical Institute at the University of Alaska Fairbanks, Santosh Panda, Research Associate at the Geophysical Institute at the University of Alaska Fairbanks, Kevin Schaefer, Research Scientist at the National Snow and Ice Data Center at the University of Colorado Boulder. And on the phone for question and answers is Dmitry Nikolsky, Research Assistant Professor at the Geophysical Institute at the University of Alaska Fairbanks. And there are also press releases in the back of the room and on the virtual press room.
So thank you. I apologize. I will be sitting because I have broken legs there under this table. So I will start, and I would like to talk about changes in permafrost in Alaska, and with some emphasis on the colder part of the permafrost on the north slope of Alaska. So there's many pictures like this. You're probably kind of familiar with that, showing that it's already thawing permafrost affecting infrastructure. Both in North America, in Alaska, and also in Russia. So I will first just show several slides with some, exciting for me photos. So this one, the top one left is Fairbanks, Alaska, right in front of the behind of the Geophysical Institute. Those three pictures were taken from Russia in different places, and thawing permafrost here impacting different type of infrastructure. This is example from the north slope of Alaska. It's a gravel road which was not in use for the last 30 years. What you can see what happened to gravel road if that's not maintained. This is the latest example from this spring, last spring and summer. This is only highway on the north slope of Alaska. Dalton Highway was actually it was destroyed in some parts by thawing permafrost and some water. So that's another picture of a road. It was road, and now you see how it looks like. So if people ask me, well, how's permafrost in Alaska? What you should expect? In the very near past, I would say, well, in the interior of Alaska, permafrost is pretty warm. It's just 1-2 degrees from thawing. That's why this permafrost is less stable. It's a really good chance that we will start to see, and we're already seeing degradation, thawing of permafrost in the interior of Alaska. But on the north slope, permafrost is cold. We shouldn't worry about it. It's -6, -7, -5. Well, during this century, nothing would happen. That's what I would say about 5 years ago. So I cannot say it anymore. And that's what I would like to kind of give you more material on that. So that's why I want to talk about north slope of Alaska, which is, we have this sites, we're measuring temperature and permafrost for the last about 35 and even a little bit longer years, and it's continuous measurements, it's unique data. And this graph here is showing this time here from late 70s to up to now, up to today, and this is temperatures in degrees Celsius. And you see that it was more or less constant warming at 20-meter depth in the permafrost. And I will be kind of emphasizing this side, Dead Horse, which is one of the northernmost sites of our measurements, where at 20-meter depth, temperature increase is almost 3 degrees Celsius for the last 35 years. So for the last 30 years, we have these continuous records where this green line I already showed you, and there is more information here. So the black is air temperature. This is mean annual temperature, air temperature. The red is mean annual surface temperature, and blue is mean annual permafrost temperature. And you can see that comparing these graphs, you can definitely say that on the long term, the warming of permafrost is following warming in air temperatures. So the main forcing which make permafrost warmer on the north slope of Alaska is increase in air temperature. But if you look at the more carefully with the numbers, so we started in mid-80s, and the temperature at the permafrost surface was about -8. So now it's somewhere about -3, and even a year before it was, well, alarming, almost just a little bit colder than -2. So this well, very strong warming trend make it kind of me wonder what we should expect. And what I did just very simple thing. So I took this 30 years of records of the permafrost temperature, surface permafrost temperature, and I just linearly extrapolated into the future. So if permafrost will be warming at the same rate, by the year 2050, it will cross this threshold, this very definite threshold for permafrost, 0 degrees Celsius, and permafrost will start to thaw. Well, that's maybe a little bit too simple to make this kind of linear extrapolation. That's why I will show you a little bit more sophisticated modeling exercise, what we did for the north slope of Alaska. We have a very good permafrost model, which can, if you use some kind of forcing, which we use, in this case, we use some projections actually to compare them, two projections of the last IPCC, from the last IPCC report, and different RCP, right?
Yes.
Yeah, RCP 8.5 and RCP 4.5. And I will compare these two projections, and you will see that actually 8.5 is like business as usual. So that's what we should expect with warming if we will not do anything about emissions. And 4.5, that's will need some kind of efforts from the global community. And you will see how, specifically for the north slope of Alaska, these two projections are really different in terms of what permafrost will be doing. So that's our interest area of north slope of Alaska. This is Brooks Range here, and results are such that, so on the left here, so it will be 2000s, 50s, and 90s, so end of the century. On the left is 4.5, so kind of moderate projections, and on the right is 8.5. And the colors showing permafrost temperature at the 2 meters, well, ground temperature, annual ground temperature at 2 meters depth. So if you look on the left with 4.5 scenario, well, permafrost is still there. So in this kind of, if the climate will be changing according to this scenario, so maybe I was right saying that, well, probably it will be warmer, much warmer, but it still be stable. So the zero is about this white color. So anything orange and red is already above 0 degrees Celsius, crossing this threshold. So for this scenario, it seems like it's okay, though it's much warmer, of course, than it is now. However, for 8.5 scenario, you see that more than 2/3 of North Slope by the end of the century, mean annual temperature at 2 meters depth will be above 0 degrees Celsius. So as a result, active layer, the layer which is thawing during the summer, will be increasing again. And again, it's a very big difference. So for 4.5, it will be increasing, but for 8.5, it will be a very dramatic increase. And the lower graphs here show very interesting results here. It's the layer which will not freeze during the winter anymore at the end of the century. And for 4.5, it's only very, very southern part of foothills. Could be developed this kind of layer which will stay unfrozen for the entire year, it not freeze completely. But otherwise, all other area of North Slope will be, well, more or less normal permafrost with complete freeze up of this summer thaw layer. In case of 8.5 scenario, more than half of the North Slope will develop this layer at some cases as deep as 5 and more meters, which will never freeze, and it will be in thaw conditions all year round. So we call it thallic, but it doesn't matter how we call it. It's really crucial for all kind of processes, including biogeochemistry, decomposing of organic material, all kind of things. So again, very, very dramatic difference if it will be 4.5 or 8.5. Now, as a result of this thawing, the surface will be subsiding. And we made very rough estimate how much the surface could subside because of thawing permafrost. And again, this is comparison of two scenarios with 4.5 and 8.5. So 4.5, you see, most of the area, well, it will be subsiding because active layer summer thaw will be a little bit deeper, but most of the area, this subsidence will be not more than 20 centimeters, so pretty small. And only very, very southern part in already Brooks Range foothills will have a little bit more subsidence. In case of 8.5, it's very different picture. So we have at least half of the North Slope will experience this subsidence of the surface, and this subsidence could be again as large as several meters. So very, very different results just because of two different scenarios of warming. Finally, I would like to show some results from the same series of models showing what disturbances related to human activities how they can impact permafrost together with warming. And we choose for this particular presentation, we choose to show you some results, assuming that the most common disturbance from human activities is the gravel pads. So any kind of construction starts with gravel pads. So what's shown here on the left side, it's developing of this layer with unfrozen layer, and like I showed this already. So in normal conditions or natural conditions, the situation with this thawed layer is like this. It's shown on the left on the lower slide. So on the right, for the same time, end of the century, it shows the thawing if we'll put 60 centimeters, 1.2 of gravel and 1.8. So depending on the thickness of this gravel pad, the results will be different. And we see that the huge difference, just putting this gravel on the surface, we see already big impact on permafrost, additional impact, additional to the climate warming. So combination of human impacts related to construction of any kind of infrastructure together with warming will make this kind of summary or impact, which will be much larger than just warming of climate. So now at my last slide, and I showed on the left the same what I just showed you and discussed, but this is for 8.5 scenario. So now again, if we look back to this 4.5, it seems like, well, in this case, these gravel pads will not be as kind of disturbing for permafrost if we will be able to keep our warming, well, relatively not that as large as business as usual. So again, this is good illustration how in a particular place, North Slope of Alaska, permafrost will or will not degrade by the end of the century, depending on what, well, global community will be able to do about increase in CO2 in the atmosphere. So I think that is my last slide. Yeah, thank you very much.
Good afternoon, everyone. Thank you for joining us for this press conference. I'm going to talk about a project that I have been working on for last few years. This project is a collaboration between University of Alaska, Fairbanks, and National Park Service, funded through National Park Service. My project is about national park units in the Arctic, and the study area, it consists of 5 different national park units listed in here, and also it includes Silavik Wildlife Refuge, which is the southern part of it. So based on limited field observations and ground data, we knew that permafrost is continuous in this part of Alaska and present everywhere except under deep water bodies. But we didn't know how the temperature is spatially distributed and how the spatial distribution of permafrost temperature may evolve in the future. So we did a modeling study to first to come out with a map of permafrost temperature distribution, and then to see using if we force our model with the climate data, then how the permafrost temperature might change in the future. So our findings were, at present we see almost 99% of the study area is covered with permafrost, and which could go down to 89% by 2050, and then 36% by 2100. And there will be places where permafrost temperature would be as high as 6 degrees centigrade than the present temperature. And talics, what Vladimir was referring to, basically unfrozen ground below the active layer, that will be widespread in most of the parklands. Our study product was 30-meter resolution maps of permafrost temperature, permafrost presence, absence, and active layer thickness. And for this study, we used a 1B greenhouse gas emission scenario, which is the balance between, you can say 4.5 and 8.5, what Vladimir showed. So I'm going to show you some of the study products. Right now, what you're seeing is a permafrost. Well, it's a ground temperature map at the bottom of active layer, and the different color represents the temperature range of ground. And the red one, that represents the presence of talic. So in 2000, and then this is at the decadal time scale. At 2000, we only see a little bit of talic in the southern part of the study area. That's about it. But by 2050s, the climate model suggests 2-degree warming by 2050s in this part of Alaska. And with that warming, we're seeing the permafrost distribution will come down to 89%, and there will be a lot of talics in the southern area. So red is mostly talic. And that could be the distribution in 2100. And it looks like 36. There will be only permafrost within 36% of the study area. And here I'm talking about permafrost immediately below the active layer. Now I'm going to show you a few pictures of what kind of impact could happen, what kind of landscape reconfiguration you could see because of permafrost thaw. So here in this picture, what you see, the linear features, those are ice wedges or impression of ice wedges. There are a lot of ice in Arctic ground. And because of the air temperature, warming in air temperature, the ice could start to melt, and once the ice starts to melt, it will create a small depression, micro depression. Water accumulates in those depression. Once you have water is going to absorb more heat in summer, and the cycle fits itself, and a small pot can start growing, and later in the later stage it could look like this. It's going to expand. There is no way it's going to stop. Here is another picture of seem like peat and troughs because of thermokarst development. And this is a different kind of thermokarst. It's called retrogressive thaw slump. In the national park area, there are a lot of retrogressive thaw slumps that have been noticed in last decade. This particular one is located on Noatak River, and National Park Service, they are actively monitoring this particular one. And based on their research, they estimated that this particular one, retrogressive thaw slump, may have started late 1990s or early 2000, based on their 3 years of monitoring of this particular site. With that, thank you for your attention.
My name is Kevin Schaefer. I'm at the National Snow and Ice Data Center. Today I want to talk about a permafrost forecast system. The United States needs a permafrost forecasting system. Forecast is essentially you take data, you merge it with models, you project those out into the future, and you get a forecast. A good forecasting system needs good data, so we also need a permafrost monitoring network. To be clear, the United States has neither of these right now. Now, what would we forecast? Essentially, we would forecast permafrost temperature, thaw depth, and we probably do this in a 1 to maybe 10-year time scale, and we do this annually. To get an idea of what to look for, my colleagues have done some excellent work. I think what they showed is a fair example of what a forecast would look like. Now, to get an idea about why one would need a forecasting system at all, you have to understand that permafrost is like concrete. It's hard, tough, and resistant to erosion. And to illustrate this, I show a picture of a colleague of mine who accidentally froze his drill bit into the permafrost and had to go back into town to get a jackhammer to get the thing out. Naturally, the drill bit did not take this treatment kindly. Now, ice within the soil acts like cement, and it binds the soil particles together. Permafrost is hard, tough, and resistant to erosion. But if you thaw a permafrost out, the ice changes to water and the permafrost changes to mud. And it's this really drastic change in physical characteristics that produces impacts to the ecosystems, to the hydrology, and to human infrastructure. And to illustrate that, I got some pictures here. These are some lakes in central Alaska in an area called Yukon Flats. And underneath each lake is what's called a thaw bulb, a layer of unfrozen soil. And as temperatures have warmed up, this thaw bulb has gotten deeper and deeper until eventually it thawed right through the entire permafrost layer, and the lakes drained from below like pulling a plug in a bathtub. Now, permafrost has large layers, blocks, and wedges of pure ice. And when permafrost thaws out, this ice melts, the water flows away, and the ground above it collapses. And we saw some excellent examples a second ago, but this illustrates, this is just a thermokarst feature. There's an ice wall melting out here, and this is on the north slope. You can see the pipeline there. This induces a great deal of change, erosion, impacts to hydrology, impacts to the plants. But it's also infrastructure that can be affected. Now, the buildings and other infrastructure are all built assuming the permafrost is going to stay solid. Now, this is an example that picture that Vladimir took. This is a building in Siberia. It thawed the permafrost underneath it, the foundation shifted, and the building collapsed. Now, to be clear, this building could have collapsed and probably collapsed because of bad building practices, but this is the kind of impact to infrastructure that we could expect with large-scale thawing of permafrost. Now, in the lower right, what you see is a village eroding off into the ocean. Now, as temperatures have warmed, the Arctic Ocean has lost sea ice, and this has increased wave action, and the waves have increased erosion rates. And this particular village is located on one of the Aleutian Islands, and the erosion was so great that the village literally eroded into the ocean and had to be moved. And it's not the only village at risk of this, and there are villages all over Alaska also at risk of having to be moved simply because the permafrost is thawing. Now, an idea, who would use these kind of forecasts? Well, any kind of group or organization that has to oversee or manage resources, land resources, manage the land, maintain or build human infrastructure. These are all target users for a permafrost forecasting system. For example, local communities, they invest a great deal of resources into building infrastructure. They need to know what's going to happen in the future. Any agency, federal or state, that manages lands, and I think Dr. Panda's example was funded by the National Park Service. They need to know what's going to happen in the future in order to make plans. Private corporations and industry, they build, they invest, they want to do business in Alaska, but they need to know what's going to happen to the permafrost. And last but not least, the scientific community itself. We need to know what's happening or might happen in the future so that we can evaluate impacts on a larger scale. Now, why do we need a monitoring network? For the simple reason is that you need good data to drive a forecasting system. And this is an example of a monitoring network of boreholes. This is run by Vladimir, and you saw some data earlier. Vladimir and other scientists have spent a great deal of effort to successfully integrate a number of these networks into a global system of coverage. And I think it's an incredible achievement. But there are still some gaps. For example, here we have gaps the size of Colorado in Alaska. In order to do an effective forecasting system, we need to fill these gaps. Also, these networks are all essentially volunteer networks. They're funded entirely by research money. And quite honestly, this is not a long-term sustainable funding model for a monitoring system. So we need a national monitoring network. Now, I'd just like to wrap up by saying that well, I can't remember exactly what I was going to wrap up with. But anyway, I know what I wanted to say. I'm sorry, it's been a long day. My brain is wandering. But I would like to say that what I would like to see is for the United States to change from a reactive viewpoint to responding to change, to an attitude of planning for change. Because without a doubt, if we plan, we could avoid the worst of the impacts, at least to human infrastructure, or we can make plans, and this will minimize the impacts to the infrastructure and the ecosystems, which I think is a much more effective way to deal with things and a cheaper way than trying to respond to change. Thank you.
Thank you. We will now open up for questions and answers. Are there any reporters in the room who have questions? Please raise your hand and state your name and affiliation, please.
Ned Roselle, Alaska Science Forum. Vladimir, kind of a two-part question. Why did you think you'd never see that North Slope permafrost thaw
in the past?
And do you remember the moment or the data you saw that made you think that maybe you would?
Right. Well, that was not only my opinion, it was a collective kind of opinion that it will never happen during this century. And at some point, maybe about 10 years ago, looking at this, extending more and more these records, longer and longer and longer, and also looking at the dynamics of climate, it seems like climate start to kind of pause with warming, and according kind of long-term trends, it seems like it's supposed to get colder. And like 10 years ago, I was thinking about present day. And at that point, I told myself so that if the permafrost temperature will continue to increase, it will convince me definitely in global warming. And that was first step. So after these 10 years, I'm convinced. Now the next step was just look at the rate. And if 10 years ago we had much shorter period of measurements, and it was kind of dangerous to extrapolate it into the future. Now we have 35 years, 40 years of data. it's about 1/3 of a century. And well, extrapolation already makes sense. And simple extrapolation into the future is also our knowledge that so far we actually developing in the 8.5 scenario and maybe even a little bit above that. So that make me change my mind, and now I can't say that permafrost is safe during this century on the North Slope.
Are there any other questions from reporters in the room? Are there any questions on the chat? Go ahead.
Excuse me. I have 4 questions from Yareth Rosen from the Alaska Dispatch News, and therefore Vladimir Romanovsky. The first question is, can you say more about oil development and permafrost? Is Dead Horse now getting accentuated thaw because of gravel pads, roads, and possibly urban heat island effect?
Yes, of course, like I tried to show in the last slides, that impact of combination of increase in air temperature or warming climate and development of the area, this cumulative impact is much stronger, much larger than just each of the components separately. So it's no doubts that this infrastructure which already built and maybe planning for the future on the North Slope, it definitely will accelerate permafrost thaw. So we definitely have to look at this cumulative impact of both climate change and development of infrastructure. And that's not only in Alaska, it's pretty much circumpolar. The same problems in Russia, and soon problems will be in the Nordic countries and Canada. So it's international problem.
And how deep below the surface are your temperature measurements?
Along this transect, typical depth is about 80 meters, 80 meters, so about 250 feet.
And do you have any ideas what will happen to North Slope oil development as permafrost thaws?
Well, I can expect more problems with thawing permafrost and failing an infrastructure, and depending on how, well, it is a very valuable infrastructure. There are some engineering solutions how to fix it, but these solutions will be more and more expensive. I would expect that the infrastructure will still be functioning, but with much more expense with much more expense compared to what they have to do now.
As part of that question, she also wanted to know if future oil development is safe.
Well, it depends if it's. It depends how it will be planned. Again, right planning, and that's what Kevin was talking about. If we will have this kind of system, if we will have knowledge, we can use this knowledge for safe development. Again, it could be more expensive than it was in the past, but it's still possible to do it safely for the environment. Of course, with further warming, it will be very difficult to keep permafrost in a frozen state just because of climate change, but at least we can minimize the impact of the infrastructure on permafrost. That's possible. Again, there are some engineering solutions. They will be more and more expensive. That's probably why we should do it sooner than later, when it's still frozen.
And just real quickly, she wanted to know if the 30-year-old abandoned gravel road was the Hickle Highway or something else?
Pardon me, I lost.
I guess there was an image.
The figures, the photos.
She asked if the 30-year-old abandoned gravel road.
Oh, okay. This is the gravel road towards the material site, which was used during the construction of the Dalton Highway and Alaska Pipeline, and it's about 70 miles north from Tulik Lake.
Thank you.
Liz O'Connell, Frontier Scientists. This year, the Hall Road was closed down for several weeks, which became an expensive thing for development up in Alaska. Was this a permafrost problem, or was it a hydrology problem? What happened there?
Well, it is combination, and really nobody knows exactly what happened. And we're trying to figure out. So there is definitely several processes kind of overlap. I showed slides in the beginning of my presentation, and last two of them were actually this piece of Dalton Highway near to Death Horse. That's exactly that's the case. And what happened, it was early melt of ice, and water came out of Sagwan. Well, it's very long. We call it Sag River, just for short. It goes along the Dalton Highway. And it happened actually in late March, which is very, very surprising. It never happened. Well, at least I don't remember this kind of situation. Maybe I just don't know everything. But yeah, and then it continued in April. The flooding, which damaged a pretty big portion in pieces of Dalton Highway. And it was a combination of early melt, then unusually lots of water in the spring, and also the way where this water went, it was very unusual. So now, first of all, of course, there was expense to repair, to open it, and now it's even extra expense because they have to put much higher gravel pad, I mean, the basis for the road. So that occasion was very expensive, and we still kind of try to figure out what exactly triggered this thing. But the final result was thawing of permafrost, very icy permafrost under the road. And on these photographs, you could see the ice which was melting and making this huge damage to the area around the highway.
Are there any other questions in the room?
Ned Roselle again. So the graph you showed at first, Vladimir, it shows permafrost temperatures at 20-meter depth at Dead Horse, right?
Right.
Are you surprised with that rising at all, that sort of tracking air temperatures? It seems like 60 feet, that would be a lot of sort of insulation from the air. Are you surprised that it's mirroring that surface temperature?
Yeah. Well, the thing that we are talking about long-term changes here. So if you look more carefully, you will see that in air temperature there's ups and downs, very significant interannual variations, we call them, several degrees Celsius. And temperature at 20 meters not following these short ones, definitely not. It's kind of integrative result of long-term changes. So permafrost reacts, and this is pretty of permafrost that we can use it as a for indication of climate change, because all this interannual variability filtered out, and we see the long-term trend. In the long-term trend, there is no surprise because changes at the surface in a year or year and a half reach the depth of 20 meters, and on the long run, it is following. And only surprise is that why just air temperature? Because there's many other things. Snow, for example. Snow is very important for permafrost temperatures, or vegetation change, or hydrology. Well, it seems like, at least for this period of time, snow was changing, of course, but there was no trend. There was no decrease or increase of snow. That's why we don't see it in a long-term trend. The same with vegetation or hydrology. So far on the 30 years time scale, 50 years time scale, pretty much what we see is impact of warming in air temperature.
George Drake from the Tahoe Mountain News in South Lake Tahoe. I understand that Dr. Romanovsky sort of became a believer in global warming in the last 30 years. Is that a trend that you can say is common, or were you a latecomer?
Well, I cannot talk to entire community. I can talk about my colleagues maybe a little bit, but again, it's well, I can definitely talk for myself, and I made my statement. Well, it depends of time scale. About 30 years ago, because yeah, I'm in this business for like 40 years. And about 30 years ago, maybe a little bit 35, it was not much, talking about climate warming, global change. I don't know if you remember in 70s, and it was more about global cooling and new ice age is coming. And for us as a permafrost geophysicist, we were very excited about long-term changes like glacial, interglacial, this kind of time scale. And we were not thinking about shorter one, like on the decadal type scale. And only development of our subject, changes in permafrost, made us believe that there is something happening. And from my colleagues, well, I would say, well, most of them, I think, share my point of view on the climate warming. And again, when I say climate warming or even global warming, I'm not talking about the cause. I am talking about the results, and that's what we see. And when you see it as a scientist, you believe what you see.
I think we have another question from the chat.
Yes, again from Yareth Rosen about the national park study. Are there any ideas of expected impacts to wildlife and fish in the park units?
I think so. National Park Service, they are using this product for their long-term, for planning long-term monitoring, as well as to study impact of climate change on the ecosystem and wildlife.
Thank you.
Are there any other questions in the room? Okay, are there any other questions on the chat?
No.
Okay, thank you very much. That concludes our 2:30 press conference on permafrost. And that is the end of our press events for today. We will start up again tomorrow morning at 8 a.m. With media availability on tracking ice, the latest efforts to measure the polar ice sheets. But at 4 o'clock and 5 o'clock, we have 2 blogging and social media forums. If you're interested in attending, we have a 101 at 4 o'clock and a 201 more advanced blogging and social media forum at 5 o'clock. Thanks.